government office, the level of resources provided is what? I want you to think. The number of people in government offices in the United States, in Mexico, in China, in Brazil. Is it at 1, 2, 3, 4, 5, 6, 7, 8?
More.
Huh? More than required. And because it's more than required, watch the system. I don't know where I was. I was in somewhere. I think it may have been in Brazil. I said, can I have like soap in the office? In the day, can I have extra soap or shampoo or something like this? This person had to ask this person. This person then had to ask this person. Then this person had to go over here, and then the fifth person brought my shampoo. And they said, oh, no, you can only have one shampoo a day. I said, well, charge me more shampoo, more money. Why did that hotel have 5 people for me to get a shampoo? I want you to visualize that this is what you can achieve. But this is what we call the best case, and it is not possible. You know it's not possible. Why is it not possible? Tell me why it's not possible. Because nothing has perfect flow. Nothing has no variation. Nothing has what? Every system has, to some extent, some disruption, some variation, and some issues with flow. Yes or no? So this is the best. Who, for example, when you have a role model, who's your role model? Who's your role model? Tell me who's your role model. You don't have role models? Who's your role model? No, one person. Come on, one. Your model. That is your dad or mom. You can never achieve and become who they are. You can be better, right, in different ways, but this is somebody that you set as your role model. You will never achieve that, but you use it as a role model. You cannot achieve this. Well, watch this now. Remember, I showed you width and throughput initially, did I not? This is width and cycle. Can you tell me what you see on the cycle time? So you see that the cycle time is 8, 8, 8, 8, 8. 8 is what? Raw processing time. What is at 5? What is at 5? Inventory of 5. What is my cycle time? 10. What is at 6? 7, 14, I think, right? So are you saying that at 5, my actual time, you know, I told you my son, problem child. Now, see, teach this until I make a call. Teach it.
Okay. This thing already in the base case, what happens after the critical, what is WO, W0?
Be tough on them.
What
Be
is
tough on them.
W0 or WO? So what is critical?
Maximum throughput, cycle time.
Okay. So in the best case, what happens is, if you keep on increasing work in process, what happens? So why does it happen?
Because the material will be weighted before, so it takes longer.
Okay. So that is the discussion. So next one is we are going to the equations for the best case scenario. So this is the best case performance equation on the law. The best case law is the minimum cycle time for a given work in process level, which is denoted by small letter w here, is given by
Good job, good job. Now continue.
the equation. What is that? It has two conditions. If the minimum cycle time is less than or equal to W0. Again, what is W0? So if the cycle time is less than the critical work in or critical wave, then the cycle time in that case is 1 by T0. And what is T0? Raw process time. Otherwise, it is given by the cycle time divided by RB. What is RB? So that is the one of the equations there, which you have to remember in the best case scenario. And the next equation is something similar. It is now going to the throughput. In the best case scenario, what is the throughput? It is again given by that equation. If that working process, the minimum cycle time is less than or equal to W0, then the throughput time is given by that W divided by T0. Otherwise, it is given by the bottleneck rate.
Are we okay? Remember, how many people have heard of value stream mapping? In the end of the value stream mapping, don't you say, this is my inventory time, process time, inventory time, process time, and you add it all up and it becomes your overall cycle time. And then you say, just my process time, and you put it, that process time, and divide it by the overall time, and you have what? Percent value added time. Do you remember that or no? Should I do that? Tell me if I need to talk a little bit. Everybody okay? Yes or no?
Yes, sir.
In this case, this to me is very superficial. Okay, if I take waiting time, so I'm looking at the waiting time, see? Waiting time, this is the waiting time, plus the process time, plus the waiting time, plus the process time, plus the waiting time, plus the process time, plus the waiting time. And this is the actual time that it takes the product to get out. What is this? Process time, process time, process time, process time. This is the value added. So I take all the process time divided by both. And there's a difference between the process time and the overall time, right? Why is there the difference? Because in the raw T0, we did not include what? The inventory, the waiting time. The greater the difference between value time and the process time, the worse off that system. So if I say percent value time, and in some cases in your processes, and this is what I'm going to show you. If I need to write it, tell me, okay? I promise you that your percent value time, or percent process time, is going to be less than 20, 30%, 40%, 50%, less than that. So if it is taking me 5 hours to do something, the actual processing time is no more than an hour. That means 4 hours of it is what? What we call it what? Wasted time, non-value added time. Now, from a mathematical perspective, watch this. T0 is going to get to my process time is going to be equal to my overall time when? When only I have the critical width level. Anytime over the critical width level, what am I going to have? That my value time is a lot less than my overall time. Do you see that? At 6, what happens? What was my time? 12. 10 divided by 12. At 14, 10 divided by 14. At what is 7, 8. 10 divided by 16. 9, 10 divided by 18. If you notice, what is happening? There is a wide gap between actual time that we require and the actual time that it takes the system to produce something. The greater the difference, the worse off the system. If this is 2 hours, 2 hours, 2 hours, and 2 hours, but it's 8, right? 8. But what if it takes me 10 hours? What is happening to those 2 hours? Inventory. If I have 4 hours extra inventory, there is a tremendous amount of inventory in all of the systems that you're looking at. Similarly, throughput is this equation. Throughput is W over T0 if W is less than the critical, but throughput is only at the best can be equal to what? The bottleneck rate. Who told you that? The theory of constraints. The theory of constraints says that if you get 4 people to go to a party, how soon you can get to the party is determined on the person that gets ready the latest. Okay? This is that equation. Are we okay? Yes or no? Continue, please. All right. So therefore, the values are, the cycle time is 8. If W is less than 4, throughput is where? Is equal to 0.5 when if the value is 4 and above. So 4 becomes what? Is the point between, 4 is what? The critical inventory level that allows you maximum throughput with a minimum cycle time. Does that make sense to you with regard to this equation? Yes? In your processes, you say, I want to measure. Leading indicator. I want to play around with a leading indicator. Can this become a leading indicator? The raw processing time compared to the overall time that it takes you to get out of the system. In an emergency room, if you're sitting there for 4 hours and you're seen by a physician or a nurse for 20 minutes, tell me what's happening. Tell me what's happening. 20 divided by 5 hours. 20 minutes divided by 5 hours. Is it a good system? Why? Because you are the part, and what is happening to you for 4 hours and 40 minutes. What is happening to you? You're waiting. And do you like waiting? Are you sure? Yes or no? Are your parts waiting? In the projects that you're working on, are the parts or the patients or the documents waiting? Yes or no? What is the difference between the actual processing time, the raw processing time, and the actual time? Could that be a performance measure? Right. Tell me, I showed you that's the best, right? That is like your mom and dad, that's your role model. You're never going to become them. But you like what they do, and therefore you emulate to try to be them. Who do you hate? Who's a person in your family that you hate? Who is the person that you don't want to become? Yes. Well, make it up. Make it. Yeah, in your family. Huh? It's hard? Yeah. It's not hard. Just make a name. Nobody knows your family. Just make a name up. Only use the first name.
Like in my dad in some case.
No, your dad is your role model.
Oh yeah. But there's more.
No, your dad is your role model.
Okay.
Now find me another person. What you want? Richard. Richard is a bad man. He's a bad man?
Yeah.
Very bad. You don't want to become Richard. This is Richard. That means if I have this, the best case yields the minimum cycle time and maximum throughput. Question, what condition causes the maximum cycle time and minimum throughput? Watch this. Go on. We know that. Tell me what is happening here. I want you to tell me a little bit about, this is Richard, right? Richard? Explain to me who Richard is. This system, listen, do you have a picture of his dad? Take us to the picture of his dad. Just go on back. Go back. Go back, go back, go back. This is Daddy. Okay? I want you to interpret, just like Daddy. Daddy is what? I don't know. Why is he good or bad? Why is Richard good or bad? What is it that you are looking for that you have learned? You determine that relationship at this moment in basis of what? Because we assume in every case, in this case we have no variation, we have no disruption, yes? So the only thing we're focused on is the flow. Flow. Okay? Flow. Is this flow good? This is Daddy. Daddy's good? Why is Daddy good? Daddy's good, huh? All right. I want you to look at it from the perspective of flow. Now, take us to Richard. Tell us, I know. Why is Richard bad? Because what?
Almost in the lower time as in writing out the same amount of job
That means, if I'm understanding this, watch this. You know what I'm doing? Lego exercise number 1. What did you put in the basket? What do you put in the basket? How many parts?
10.
You know what this is? That right there. You see 1, 2, 3, 4? That's 10. When I move parts down this path, this is what? I moved it in 10, 10, 10. So the first exercise you had Richard, the last exercise you had Daddy. What was the criteria? Everything over there was balanced, but you did balance it. Here everything is balanced. So what is the difference? What is the difference between the best case scenario and the worst case scenario? The worst case scenario, you are doing what you did in Lego exercise 1, which is batching products together. And I'm sending 10, 10, 10, 10, 10. In this case, I'm sending 4, 4, 4, 4, 4. And all of a sudden, because I am doing this, watch this. How long did it take? 32. What is your raw processing time? 8 divided by 32, what is the value added? 25%. By what? You didn't change the cycle time. What changed the cycle time? The fact that you have perfect balance. What was it, 2 hours? 2 hours, 2 hours, 2 hours, 2 hours. Oh, I got it. The other thing that you did was, you flowed the product through here perfectly. 1, 1, 1, 1. But now, it's not 1, 1, 1, 1. Forward. Move forward. Move forward. Move forward. And if I'm moving 4 and 4 and 4 and I'm batching it and it's not one piece flow, all of a sudden, because of that, what is your time? Your time is all messed up. Go on. Is it okay? All right, go on. Therefore, this is Richard's definition. See this, Richard? Richard is W. What is W? The number of inventory times T0. Throughput, 1 divided by T0. This is now fundamentally giving you what? Boundaries. Okay, take me to the equation. Take me to the next slide. I think it's the next slide is the graph, right? There we go. When you design a system, when you solve for a problem, are we okay? Are we okay? When you solve for this problem, don't you need to know what is the best case and the worst case situation? So tell me, when you are going to your projects, how do you know what's the best case and the worst case? Tell me. See, you have to talk to me. Because if you don't talk to me, I think at 12 o'clock I'm supposed to come and grade your projects, right? If you don't talk to me and I don't like you, I'm going to say 0, 0, 0, 0, 0. So tell me. I'm going to sit here, relax, and have my coffee until you talk. Wake me up. Whatever time, until somebody speaks. You realize that it's not me that's important here. It's you. I can say whatever I want. It's you that has to interpret it in your minds. So what is the best case? Tell me the definition of best case.
More throughput and less circle time.
What creates that? Can I tell you the following? I assume that all people like me and are going to work in the system. I assume there's no disruption. I assume that there's variation. I assume that there's a balanced line. And I assume that I have single piece flow. That means I have the ability to flow. I have 5 assumptions, and these 5 assumptions give me the one end of the spectrum. In this case, this is not the worst case, because I'm still assuming that all people are working. I'm assuming that there is no variation. I'm assuming that there is no, what? Disruption. I'm assuming that it's still balanced, isn't it? 2 hours, 2 hours, 2 hours. The only thing of these 5 things that I'm changing, one small thing, is I'm now batching it together. And the use of batches allows me to take you to the worst case. And it's a fixed amount. 4, 4, 4, 4, 4. If I do that, I have the worst case. How many systems in your country batch things? That means I will write 5 documents and then forward to you. I will see 6 patients and do something. If I batch this system and I don't have a good balance, watch this, in which case most systems that you have don't have good balance. If I have disruptions and I have variation, and there are certain people that say, oh, I don't care about this job, I'm just sitting here and doing nothing. What kind of a system do you have? If these are the 5 criteria: engagement of people, disruption, variation, and in flow, we're talking about balance and one-piece flow. And I'm only changing one thing from best case to worst case. Are your hospitals set up with the following? Single piece flow, balanced, tell me. No variation, no disruption, and everybody takes care of their job. Yes or no? Is your airport set that way? Is the government offices set up that way? Is your university set up that way? So they're not even richer. You know who they are? There's some guy from a prison that we brought in. Tell me about this guy from the prison. Just make up.
This guy kills people.
Kills and robs people. You live every day with a person that kills people and robs people. And you're okay with it because we don't have fundamentally the ability to distinguish between that and that. Well, is this helping in your design? Say yes. Alright. See, continue the work. Oh my God, practical worst case. That means this is still not practical. This is not realistic. Why is it not realistic? Tell me. Because I am not considering this. I am not considering this. I am not considering this. The only thing I'm considering is the flow, and the only thing I'm considering is, watch this, I'm only playing with one factor. Of the 5 factors that in my opinion are key factors, I'm only playing with one factor, and I'm showing you the impact of this one factor. And majority of what you are looking at in systems are batching those things. Not every one of you. How many systems do you know that you're looking at for your projects that are batching things? Say yes. You're not even looked at balance. You're not looked at variation. You're not looked at disruptions. You're not looking at anything. Watch, see, when solving the problem, you solve it not because I see something. I solve it because I have a template in my mind and I look for things. You are not somebody that does it by looking. You are a physician of systems that by the first question that you ask the patient is the following. What is your throughput? Tell me about your inventory. Tell me about your cycle time. Is there a big difference in between raw processing time and the actual processing time? What, and then depending upon what they answer, you say, is a flow a problem? Is this a problem? Is this a problem? And you can take them down, take them down, take them down, and you now have a systematic way going from patient to patient to patient and fixing those because each one of them is different. Show me the picture of this prisoner. Don't show me the equations. Do we know, you don't have a picture? That's okay, that's right. You know the difference? In the first one, what did we do? 1, 1, 1, 1, 1, right? In the second one, what did we do? Fixed. 4, 4, 4, 4. What if I,
Or this is simple, just
just let me go to the NIV. What if I didn't have 4? What if I gave you 1, 3, 6, 2, 5, 1, 3, 6, 5, 6, 6? What if it was random and if it's not fixed? Is random better or fixed better? Take your hand out like this. Put your hand like this. Now take your other hand and hit it. I'm going to ask it one more time. This is a critical thing for you to think. Is 4, 4, 4, 4, 4 good, or it is randomly 1?